right, so this is MERA, Trading Position for Performance, a work done at Software Campus or with the support of Software Campus. Let me just jump right in. So I want to take a step back at the beginning of the presentation and ask why we use Flink. And I think the why is it's easy to compute chain of functions of a large, like masses of data. And it does so while being fast, cost-efficient, and accurate. And it shares this property with most big data systems. So it accomplished this by using those very basic task abstraction, which is basically a queue and a processing thread and another queue, and deploys this by the hundreds on commodity hardware. In those tasks, they are connected, right? And by connecting them and exchanging information and bringing all those functions together, UDF, by the way, for user-defined function here, they do the computation. So this looks basically very simplified. It looks like this. You have a packet or record coming in, being processed by the UDF, coming to the output queue, and then finally going to the input queue of the second task. Unfortunately, those commodity hardware is failure prone. So it might happen that the output queue of the second task will be full, like you can see here on the slide. So in that case, the records will stop at the second task, and the queue will run full, and also the queues of the first task will run full. And that means that the connection will be blocked. A phenomenon that we describe as backpressure. And it's not only, and this is interesting, it's not only going backward, it's also going forward. So at least in some versions, you have a you have a round robin mechanism that determines where the next record goes to. And when the next task is blocked, then the previous task will wait to send the record to this task and will not be able to switch over. Now, for now, I just describe those failures as belonging to the commodity hardware. But there are many reasons for that. There are slow hosts, which would be a typical hardware or software failure. Then there's slow network links, in this case an uplink. There is data skew, as we have heard in the last presentation. So one key group gets a load of data. And then there's also simply the logic that differs. So you have a very fast UDF connected to very slow UDF, because maybe one of them has very complex logic while the other one has very simple logic. So in principle, you could catch this by changing the degree of parallelism, but that means that you have to know, what the right degree of parallelism is. And with MapReduce, that's kind of simple. You simply rerun the job, you create a job profile, and then from this job profile, you get an idea how to tune the system. And if that doesn't work, you can also go back to speculative execution. So you just rerun the same tasks multiple times at the same time, and then you take the task or you take the result of the fastest task. So that covers when you have a few stragglers in your system, a few tasks running really late. But yeah, we are using Fling, and this applies to batches where you can iterate and where you have short-lived tasks. But this does not necessarily work for streaming. And that's because data streams are different. In principle, we would want to have something that looks like this. Perfectly even load, spread out over the time, and we can just consume it and just concentrate on making the system itself hard. But you can have skew, and you can have very high skew in the load. And not only in the load, but also in the content. So you would see that at this point you would think, oh wow, then I'll just have to have 3 nodes for the one key group and 1 node for the other key group. But then at a moment later, this can completely change. I'm not saying it always changes. Of course, there are patterns, but in principle, it's unpredictable. And if you have a flash crowd, for example, in e-commerce, there might be changes. So there's no perfect configuration. So coming back to the beginning, we said there's three things that we treasure. We treasure speed, we treasure cost efficiency, and we treasure accuracy. So can we trade off some to be like for the other? Well, we probably don't want to trade off time because we have consuming applications that rely on these results to be in time. And yes, we could throw more money at it, but that would mean that we always have to scale to the highest load peak possible. Well, of course, here in Fling, we talk a lot about dynamic rescaling, but still at that time, when you rescale, that means you have to make a save point, stop your job, and then reload the whole thing. And that means also you have to provision a new machine and you have to migrate the state. There are ways to optimize that, but there's always going to be some kind of overhead. So what I'm focusing on here is to reduce the accuracy. And the reason is that what I'm going to show later in a few slides is that you can change the accuracy pretty fast to react on a peak in a load, which you cannot do with the other methods. So that's sort of the way I go here. So what can we do for reducing the accuracy for better speed or better performance? Well, there's approximation techniques, a few we heard in the last talk. There is aggregation. You can combine records, and then you have fewer records, and that means you are faster. But in reality, when you have tuples and they have a schema, then you have to really make function that combines both schematas together, which, if you have many columns, can be very complicated. And so, yeah, it might work for a specific use case, but it's not very easy to generalize. So I'm looking at the second part. Now, if you have attended the last Fling Forward last year, there was a talk about stream aprox. In stream aprox, the authors argued that you could always rely on simple sampling to reduce the load in the system. But this has the big disadvantage that it would not that in the end result, the small or few numbers of items that belong to one category would not be represented. So if you have categories inside of your stream, you really want to first categorize them and then sample based on the categories. So the idea here is to generate a representative subset. And that's a good method, but it does not necessarily work for all cases. So at some point when you do a log-based analysis, you maybe really want to make sure that some part of your log stays in the result. So you would not want to trade off or not want to lose any error or warn messages, but you could live with the occasional miss and debug messages. And there might be other use cases. If you look at sensor networks, there too, you might have a very important heat value, and you want to really see if something's burning, but unless other items or other records you could spare for time. So that's where we developed another method, which we call load scattering, and I know this term is heavily used, but you could also call it priority-based filtering if you want. The idea is we are very simple. The user defines a priority score. The items are then given a score by this function. And then in the load scatter itself, we can simply move a threshold up or down to define how many items end up in the result set. All right, and both of these methods have the advantage that you in principle can change the rate at which they operate during the lifetime. And this is exactly what we are looking at. So we introduced MERA. MERA is this idea to place those kind of approximate tasks in your pipeline and then leave it to one system to do the analysis. And so we collect all of those metrics. They are accessible via the task managers in Flink. We store them internally in a sort of a graph representation, and then do an optimization with an integer linear program, and then push those as target rates back up to the system. Right, and we also developed, which I want to show you right now, a monitor system where you can look at how this works in real time. Right, so principle, this is our monitor, and you might be like, this is a new way of presenting the tasks. I mean, different to, not fundamentally new, different to the rest of the presentation. So just gonna explain that for a second. The balls that you see, those are basically the tasks, and the left and the right half of the ball to show the saturation of the input in the output level queue. We just use this very minimalistic representation to make it easily scale to many nodes. Not saying it scales to 1,000 of nodes, but for our use cases that fits. And similarly, on the left, you see like how they are distributed across multiple hosts. So ideally, you should be able to look at this and see what is going wrong with your job and where the problem is. All right, so let me try to switch over to the actual presentation, the demo. If we have internet. Otherwise, I'm just going to use. Right, okay, so I'm just reconnecting to the Wi-Fi, see if that works better. Okay, I'll give it a last try. I'm just gonna try to use my own device, like my hotspot. That looks to work. Right. Just connecting. Okay, in principle it's connecting, but yeah, so friends told me I should bring a video presentation, and I said, no, I'm gonna do it live. Okay. Yeah, I think so. Right, okay. So that's basically the idea, that the graphical interface that we see at the moment. So the idea here is that you have a few. So we have introduce a custom delay at the end of the of the pipe. You see it over there, and then we record the latencies, and then the load shaders, which are defined, which are named as load shaders here. They'll then increase the drop rate depending on rises in the queues and in the latency, which should be about. Okay, so what you can see here is that the bottleneck rate is increasing, and then also the drop rate is increasing. And in principle, you should also see the queues rising up. Just check if there's well. Okay, so, but basically that's the idea. So you have, compared to Grafana or the Fling UI, you really have sort of the big picture perspective, and you can say, well, it's this mapper over there which is making the problem, the queue is running full, and then you can see the effect immediately. Ah, yeah, no, yeah. Okay, and yeah, so that's the queue is running full, and then like if now the drop rate is like increasing as well as we run empty again. And this way you sort of have the big picture always with you. Okay, so I think I'm running out of time, so I'll just switch over to the other presentation again. And right. Right, so that was the short demo. Sorry for the intermission there. That's the idea what we're working on. We're building this onto 3 insights. That dynamic approximation is faster than scaling. That backpressure handling must be handled everywhere in the job and not just at the source. And that there's more to approximation than sampling. So there are other methods that we can use even when you think that sampling is not for you. And I just want to also thank the group that helped me. So this is the team that worked at it. So thank you.
Thank you very much, Niklas. I think we have time for some questions.
So is this the prototype, or this is some project can I use it for a project, for example?
Well, we have the code and we can talk about it.
Okay.
So I mean, as with any prototype, it's in development and it's rough around the edges. But you know, this was a real Flink job running there. So sure.
Okay, great. Thanks.
So I guess not every data set is compatible with having the quality of it reduced. I wondered if you had like very particular great use cases in mind for the degradation.
Well, I mean, the thing is, can you throw away some data? That's the question. If you have a sort of transaction workload, no. If you have some banking workload, no. That's not possible. But if you go into the sensor readings and you get many readings multiple times, then yeah, there might be somewhere. So the big idea that we have there is just you really might want to have this precision, but you don't need it necessarily. So it would help you, but it's sort of it's sort of the trade-off. When you're in this situation, then you can use that system, and in the ideal case, we're not there yet fully, but you could plug in your own approximation, and it would just feed the rate it should apply at the escape moment, right?
Could you also apply this to, let's say, parts of the job only? Assuming you have one sink that is serving the dashboard, live dashboard, there you can probably afford to lose data for the sake of monitoring. Whereas you have a really transactional sink where you want your data to end up eventually.
right? So the idea here is that you can, I skipped that, but the idea is that you can just place them where you want, and again, it's a work in progress, but what we have here is, like, those are the places where we define we want to have load shedding. Now, if you say in your job you cannot have it here, you can only have it there, well, we would leave that to you. And if you say there's this place in the dashboard that it makes an effect on the whole job, and then just place the load shedder there, and we'll try our best, or the optimizer will try their best to use that to improve the result, the output rate.
I guess the difficult thing will be that your the part of the job that requires every event to be there will also slow down up to the source, so the combination might be...
Right, so I think you can only do as good as, you know...
So 2 jobs would be for this example, would be best for this example.
Depends on a real topology. I mean, sometimes, as I said, what I'm trying to show is also, you can't just put a load shedder in the beginning and then sort of, you're done. Of course you can do that, but if you place it somewhere later, you have much more opportunity to also even out imbalances in the system. And so that could help.
Okay, I think that's it for time. Thank you very much, Niklas.
Thanks.